Yeah, so I work for the EPA in research and development, and what we do is provide a lot of support, model support, data generation support for the different regulatory offices that are in DC. And so this is a project to help the pesticide regulators here in the US do modeling of pesticide runoff, but in particular in urban areas where we have a lot of expertise in agricultural areas, but a little bit early days for getting the pesticide runoff right in more urbanized areas. I'm substituting for a couple people. This has been a good project for people getting jobs. So Sumati Sinatambi originally worked on this project and actually went to work for the federal regulators in DC that last year about this time. And so Emma Chelsvig was a research fellow that was working on this year. Well, she just started a new job 2 years ago. 2 weeks ago, and so she just left. So I'm filling in to provide this presentation. But here what we're going to do is look at deterministic and probabilistic approaches, Monte Carlo approaches for the pesticide water calculator to simulate bifenthrin concentrations in urban runoff. We're using sort of the in-house model for this, PwC, which is the pesticide water calculator. And so this is, we also want to look at the SWIM model, which is more of an urbanized stormwater management model, and SWOT model as part of this project. We started with the model that gets commonly used by the agency to estimate pesticides in surface water and streams in particular. This takes place in the San Joaquin, Sacramento River Delta. It's a pretty well-known habitat for fish and invertebrate species in the Central Valley of California. So it has a lot of impact. Central Valley is a very productive agricultural system. And this area also has a lot of well-known threatened and endangered species in the US, including a history of some of those species being impacted by pyrethroids. And bifenthrin is sort of one of the more toxic pyrethroids in this area. It's an insecticide that's used by homeowners and professional applicators to sort of treat so it's used more in urban situations. It's heavily used in foundations, and in landscapes to kind of protect areas from insects. And going back for the last 10, 15, 20 years, you have measurable amounts of bifenthrin in urban runoff and in the streams of this area, like 60, 70% detect rates for these different situations. So we're looking at the upland urban areas in this Sacramento-San Joaquin River Delta, and ultimately looking at impacts to some fish that are of important in this area, including the Delta spout. So we want to get into fate and transport relative to agricultural areas. These urban areas have a lot more spatial variability, a lot more landscape variability, a lot more differences in pesticide use patterns and rates. They're not as uniformly applied. And so we have a lot of uncertainty, a lot of complexity just dealing with getting the inputs to the system right, and then how they route. There's a lot of preferential flow paths with it, which in urban environments obviously follow the built underground structure, the history of like laying sewage pipes, that sort of thing, as opposed to sort of the topography of the landscape. So it can't be just picked up from a three-dimensional model of the surface, that sort of thing. You need more underground knowledge of what the system looks like in order to route things correctly. So fate and transport of urban-use pesticides is a little bit trickier game than the more traditional agricultural applications. The model that we're using is PwC, which is the pesticide water calculator. This was originally developed in the Office of Research Development where I work at, going back a couple decades. I think the early origins of these models were in the late 1980s as sort of Fortran codes that handled the different aspects of fate transport. This prism piece on the left, essentially it's a one-dimensional transport model where you have vertical movement of water through the different soil compartments, and then the soil water contents in the columns is calculated from the amount of infiltrated water from above. And then if you get any exceedances of the field capacity, you'll get just sort of a horizontal flow into the next compartment, or you also get a runoff calculation. And so we'll get this runoff calculation that goes to the edge of field and agricultural situations, but it's more like just a stream edge and these urban environments that's received by this VBWM, variable volume water model, which simulates the water body processes within the water column, and then the sediments in the benthic region of this area. So it has a lot of classic sort of fate and transport processes. It does dispersive and effective transport, first order mass transfers, and absorption, desorption, pesticide type of processes, photolysis, hydrolysis, redox reactions, all those kind of typical reactions you get from fate and transport models once they're in the environment. Importantly, for pesticide applications, there's a lot of different ways that pesticides can be applied, and so a lot of these, everything from a spray drift, like you see with this old bi-wing airplane, to granular type of applications, or different types of soaking treatments around foundations. These are all handled with special routines in this model. So this is the big advantage. It's well suited. PwC is well suited for pesticides, but it's not a great model in terms of the spatial definition or the temporal definition over time for long-running simulations. And so we'll also be looking at swim and SWAT for those types of applications. So the site is California, Central Valley of California. Central Valley is, as I said earlier, a big agricultural production area. Tons of different vegetables are produced there. A lot of different cash crops. A huge variability in the types of crops that are produced, as well as the types of pesticides that are applied. And we're looking at sort of urban neighborhoods, urban residential areas. We modeled a few different locations. Two of them are a couple storm drains in Roseville, which is Placer County, which I'll show in a bit. And then it has the Pleasant Grove Creek watershed there. And then also Folsom in Sacramento County proper. So these aren't huge urban areas. Roseville has about 150,000 people. Folsom has about half that, but they're pretty tightly urbanized residential neighborhoods that are surrounded by agricultural fields. So here we have this complex mix of agricultural and more residential and urbanized type of usages side by side in these watersheds of Central Valley. So we have, the typical type of watershed map for Pleasant Grove Creek to handle precipitation and flow, the routing through the different subreaches of the streams, and you can sort of see the location of this sort of upper northern central California, so off the coast, but inland from the mountains. Have a lot of data. The state and the local counties have measured bifenthrin concentrations over time. So they have 6 different flow sites that we can gauge. We have a couple of precipitation gauges in the area, as well as a number of different surface water sites that have been pretty consistently measured for surface water, and less consistently so for sediment concentrations. Not a high slope environment, so it's more of a flat kind of agricultural environment for modeling the runoff, but sort of a compact soil, so there is kind of a lot of runoff and erosion type of issues. So one of the advantages of working in California relative to other states in the US is that there's a lot of records on pesticide applications. California is one of the few states where you actually have to get a permit, and there's a database, so we can essentially pull from this pesticide use database for the county and the surrounding counties, which contains this watershed, different types of pesticide applications, and massage that as sort of the inputs for the model. So what we do is those are reported monthly. We downscale that to daily with a 30-day moving average over a multi-year period, and apportion it based upon residential and industrial land uses according to this method that was developed about 5 years ago by Yuzhu Liu. who is a local regulator there in Sacramento and a co-author on the manuscript that we're developing for this. And so essentially we apportion the amount of pesticides that are applied based upon the relative contributions of the urban land covers within the different counties of this area. So this is sort of the original monthly time series. You can see, so you can see some spikes over time in terms of the amount that's applied, and there actually are some modifications over this period of time for the label, how this pesticide is allowed to be applied. In terms of the overall simulation period, we have weather going back to the 60s essentially. This pesticide use data originated in the 80s, but we only have up through 2016 at this point. And then we have concentrations that are measured from 2009 to 2017. So right now we're able to model over a 5-year period from 2009 to 2014. But we're looking to extend that into the more recent present, so through 2017 and beyond as we get the updated pesticide use applications and update the weather files and some formatting changes. So to get the local weather files, we need to manipulate some of the data. And so we're doing a deterministic model setup, which is a typical one-off that they often use for assessments, where they just use a bunch of default files, default input assumptions to estimate the concentrations, make a decision about risk in this area. But then we're also doing Monte Carlo implementation. And so this has been the big work of this project so far, is writing some R scripts which wrap the Fortran codes in Prism and then VBWM to sort of do all the accounting and manage the data transmittal, and to allow us to do Monte Carlo simulations of 5,000 or more simulations when we're going through and modeling this. So changing the assumptions for each one, that sort of stuff. And those codes, those R scripts that do that wrapping, are available from this GitHub repository. But essentially for this project, we're doing 5,000 iterations. We're passing Prism inputs, so we have 40 inputs that are uncertain overall on this exercise. To do the Prism one-dimensional transport of soils into the deeper layers of the soil surface as well as groundwater, and then runoff to the water body, and then VBWM handles those processes that occur once the pesticide hits the water and partitions to the sediment, moves downstream, that sort of thing. And so we have 5,000 sets of inputs, so we get 5,000 sets of daily outputs over a 5-year period. And so I'm going to walk you through these different results. There's a lot of information here, so I'll build it up a little bit over time. So these are percentile plots. This dark blue line is the median of the 5,000 simulations over time. So you see a bit of an increasing trend. That median is the function of increasing pesticide use early in this window. Our deterministic simulation with the defaults is actually a little bit low here, so it's a little bit below the median. And then this lighter blue, this somewhat darker blue, and this third level blue, this is plus or minus 1 standard deviation, 2 standard deviations, 1 standard deviation, 2 standard deviations, and then 3 standard deviations from that median that captures the variability in the water concentrations at the areas of interest. And then we can add in the observations. We have a bunch of periodic observations over time. These are these red dots. And you can see that overall, early in the window, the majority of the simulations are underestimating the amount of bifenthrin and surface water for this area, and then later they're over-predicting a bit. And then we have some lines for context. These are like ecological use criteria that are important in this area. So we're in this range of concern with the concentrations and with the simulation results. And then we look at that versus the application rates here. So these vertical bars are the application rates. And so you can see pulses in terms of increased and decreased use of bifenthrin, and then rainfall events. And if you look closely, you can kind of see that the median line jumps in all these situations, and that's in response to these rainfall events that's pushing water through the watershed, picking up bifenthrin and flushing it out to the receiving streams and increasing the concentrations in the subsequent days. And so this is all that information together. with the applications and as the daily moving average and the precipitation coming down from with these vertical bars from the high. It kind of explains the variability that you see over time in these simulation predictions. We have similar information for the sediment. So this is the same setup, but these are sediment results with variabilities, but we only have a couple areas where we found sort of reasonable in-stream sediment concentrations that we compare the simulation results to. But you can see they're within a standard deviation. So this is actually, we were quite surprised. We did not think this model would do such a good job since it wasn't so well set up for urbanized use. But we see that although we underestimate a bit in some of these simulations, especially early on, that across the 5,000 simulations, that is plus or minus 1 standard deviation. Most of the data is falling within 1 standard deviation of the median. So we were pleasantly surprised by the performance of the model here. And then we also did some sensitivity analysis. We just did partial correlation coefficients over the course of the entire simulation. And we got the typical, no big surprises here. We got a runoff curve number, which sort of partitions between runoff and infiltration as a big influence for the surface water concentrations. A lot of universal soil loss erosion factors, and of course the application rate as being really sensitive parameters that are important, and then some partitioning types of parameters as well as degradation end up being big influences on this concentration over time. And we can actually look at these are sensitivity by day over the course of the 5-year period. And so some of our more important parameters like curve number and some of the erosion coefficients, you can see vary, again, in response to specific rain events that are driving what's going on in this watershed. Then we get similar results for the sediment concentrations too. Again, the curve numbers and the application rates and these erosion coefficients are important for estimating sediment concentrations. And so overall, PwC did quite surprisingly well for us. We weren't expecting it to do as good as it did right off the bat. We identified some sensitive parameters. What we want to do next is we're doing an approximate Bayesian computation approach with some sequential Monte Carlo to calibrate the parameters that we have and narrow in on what we think are good ranges for these parameters to use and improve the model fit. And then we're also working with the SWIM model right now, the stormwater management model I mentioned at the beginning of the slide, which has a lot more detail about the urbanized environment to allow us to and see how that does compare to this PwC model. So that's all I have. I'd be happy to take any questions you guys might have. Thanks.
Thank you very much, Tom, for this nice presentation. Is there any question from the audience? Just a curiosity, Tom, looking at your results, it seems that the concentration and even the sediment are quite stable. So there is not a very high variability in time. Is any, yes, here you can see that it's almost constant. It seems to be in these 5 measurements that you are reporting in this graph. And if we look also at the previous graph, you have more data, but seems that they are not very much fluctuating time. Is any consideration that you want to add to this simulation? Also consider taking into account the sensitivity in the measurements, so the error that we do while we are estimating the value reporting for this concentration.
Yeah, so I would say that these sediment concentrations are pretty stable, but I would note, and I meant to point out that the y-axis is log 10 transformed. So we're actually kind of bearing some of the variability, and we kind of have some pretty broad ranges here in terms of the simulation outputs. So there is, 1 to 2 orders of magnitude in the surface water concentrations. And so this is, I've compressed it a bit by the way I presented it, but there is some sort of dynamic variability that's existing. and a kind of a bit of a trend here over time in terms of decreasing bifenthrin concentrations, and then more internal dynamics that are related to the stormwater events. What we don't have is sort of nice, in short spaces of time, measurements of the surface water variability, like you might expect after a big storm event here or here. And that's really what's missing from this as we move into swim, which allows you to do hourly simulations. So you might have a situation where you have a stream flow with low level and not much pesticide moving through the system, but you get a rainfall event, it pushes water through and it picks up the pesticides, and then you start to see spikes like a couple hours later from the pesticides that are being delivered. And that's one of the things that we've talked about that we'd like to have here is more short term, because there actually is maybe 2 orders of magnitude variability across these surface water results, just not so much the sediment. But we don't have the ability to capture that in short periods of time. And these label modifications seems to have sort of reduced. So this is an interesting window because there's been 2 label modifications that occurred during this 5-year window that sort of see a reduction from, like, you know, this is maybe 0.2, 0.3 to less than 0.01 micrograms per liter of bifenthrin in the surface water.